let's say I have a very respectable LLM, and it is taking also the ordinary, regular feedback would be, the user, you have successfully completed a squat. But the version that we are presenting, it says, smooth on the way down. It's literally useful information to me.
All right, everyone. Welcome to another episode of the TWIML AI podcast. I'm your host, Sam Charrington, and today I'm joined by Fatih Porikli. Fatih is Senior Director at Qualcomm AI Research. Before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. Fatih, it's great to have you back on the podcast. It is becoming a bit of a tradition for us to have you back on to discuss Qualcomm's research at the CVPR conference. The vision team there has been super busy. I don't think we've had quite this many papers to review for any of our conference episodes with your team. I think there's a total of 16, of which you're an author on 3 of the main conference papers and another 4 of the workshop papers. Welcome back and congrats on all the accepted papers.
Thank you so much, Sam. It's always a pleasure to talk to you at this podcast. I have been looking forward to that. We are doing a lot of great, interesting things at Qualcomm, and I would love to, talk about some of them with you. It's a pleasure to be here again. Thanks for having me,
Let's maybe start by having you zoom out and talk a little bit about what were some of the big ideas that your team has been working on since last year's CVPR.
It was very, very busy year. We are witnessing another, evolution in research. Very disruptive changes are happening thanks to generative AI. And Qualcomm is at the front runner of that, research big wave. And we have been focusing on generative AI. We did great work in taking such generative AI solutions, LLMs, LVMs, stable diffusion image generators, video question answering, everything. And in addition to those, we are extending to other modalities from speech to language to image to any other things that you can imagine. This is for mobile applications, but also for autonomous driving, for XR, augmented reality and virtual reality and IoT, robotics, anything you can imagine, we are working on critical applications as well for these generative AI solutions, in addition to what we do in computer vision and perception and everything. Yeah.
And so I think we'll dig into some of the papers that your team has worked on, and we'll maybe organize those in the way you just suggested. We'll talk through some of the Gen AI related papers first, and then we'll dig into some of the papers that are more traditional computer vision oriented around perception and motion and other things. First paper that I'd like you to talk a little bit about is the Clockwork UNets paper. Can you tell us a little bit about that paper and what it's focused on?
Absolutely. As you said, these diffusion models, in this case, it is a text-to-image generator diffusion model, and in the heart of it is engine something called as UNet. And UNet, because its shape, at this opening and closing, there are higher resolution features, and in the middle, it progressively makes the feature size smaller, and then it expands. So this is an autoencoder architecture. We have an encoder and then bottleneck and decoder. So this is UNet. It is computationally expensive because most of the computations we do in text-to-image generation, we repeat this UNet many, many times. Maybe 20, maybe 40, maybe more. So less is better. Most of the computation goes that. Anything that we can accelerate this part would be useful. So we look into UNet and we realize that not all operations have the same impact. Operations in this UNet architecture, middle layer or kind of like the initial layer or closing layer, equally important to the output image quality. The changes in the higher resolution layers, even small perturbations there would kind of change the output image. But in the middle layers, if we change them small. It doesn't change the output image quality. However, it impacts the composition of the image, overall composition, where the objects are, where the things are. So based on this observation, what we did, Sam, is we replaced the middle layers in this unit with approximating network, which is taking the previous features and the current features coming from these larger spatial layers, and then without running the middle layer, we do very simple operations, and we approximate in a way, kind of in this architecture, which provides maybe more than 30% savings in terms of flops, computations. It significantly accelerates the overall computational load of the unit.
Is it counterintuitive that the lower resolution feature maps at the center of the unit would be more resistant to perturbations? It would seem like a perturbation there would have an outsized impact because there's less information that you're perturbing, if that makes sense.
It has an impact, but it has an impact on where it's a compositional impact. It is not going to change the refined textures. So what we do, we initially run entire units. So we let kind of this diffusion to learn where to put the things based on the given text prompt. And then once it decided, okay, there will be a face here, there will be a tree here, a flower here, let's say, that object type semantics are not going to change significantly even if we perturb the middle layers. However, the bigger layers in terms of spatial, of course, these small and big in terms of the spatial resolution of the feature size, feature maps, kind of if we change them, it will be visible because fine texture is going to change. But if we change the middle layers, object will be maybe kind of slightly moved around or kind of become some different object, but on composition wise, it's going to be similar.
So the idea is that for these middle layers, once the network starts to converge on a composition, you can do a lossy approximation of prior iterations as opposed to doing the full calculation as you roll out the network.
You are correct. Yes. Of course, keep in mind that this generative model, it takes only kind of user prompt, text prompt, and it starts with a random seed point. So you actually don't know what is going to come out of it, right? And we take advantage of this fact. Yes, we change the composition slightly also, because as I said, at the initial iteration of the unit, we run the full unit, then, we borrow what we computed before. So kind of we take advantage of that fact, it is slightly different image coming out. It's not pixel-wise accurate if we run the full network, but regardless the quality, then we look at the FID scores, clip scores, it is not any less than the, kind of the full run of the unit. So maybe in some cases, it's even more preferable, even though we say cut 30%, more than 30% of the computations. Yeah.
Got it. And you mentioned FID scores and clip scores as the evaluation metric. Can you elaborate on those and what they measure?
FID score measures the diversity of the generated images. It is a distribution-wise metric. It looks at, okay, what comes out of such generative models, how different they look like. Are they generating the same type of images or different type of images? When I type a white bird, is gonna just generate the same white bird in same pose, or different type of white birds, different type of pose flying, or kind of other things. So that is the FID score. This is an inception score, freshet inception score. The other one is clip. Clip is evaluating how the generated image confirms with the given text prompt, because this score, is learned, this network, there's a clip VIT and text encoder, image encoder and text encoder, they are learned to map into the same space for image and the generated image and the text prompt to be, consistent. It minimizes the distance in that mapped joint space. So when we look at these scores, what it means that the distance FID is smaller, which means, you generate very diverse results, which is what we want to do. And also clip scores, they are higher because there's better agreement between this text input and the generated image.
For this paper, you released code as well?
Yeah, absolutely. We have now new initiative at Qualcomm AI Hub, which we take all our models, internal models, and we also provide some of them to our community, research community, and everyone. So you can access Clockwork and many other, models there. Yeah.
So the next one we wanted to talk about is Look, Remember, and Reason, grounded reasoning in videos and language models.
Yeah, we are going over our generative AI-based, papers. This one is quite interesting because it is doing something very interesting. These networks, for instance, we have, let's say, a video LLM. It takes video input as an input to the algorithm, and then there's a language model, and we ask a question about, what happened in this video. And these models are good in terms of capturing the global information, but in terms of the object-specific information, for instance, where was the object in the scene, and what was the object type, or object identity, and how object moved, like this detection, recognition, and tracking information is not very well captured by such models. But we have this a very interesting stochastic probing approach. What we do during the training, we randomly ask questions about, for instance, about this information that I just mentioned. What was the type of the object? Where was the object? How that object is moved? So we do such questions. We incorporate such questions in the training of this video LLM. So it's a multi-modal model. It's a language model that takes video as an input. And in test time, we do not need to explicitly probe such information. So then this inference, when we are asking a question, the response would be more efficient, fast, in terms of the number of tokens, inference would be short also. For instance, I can give you some examples of what kind of questions we are asking. First, one is Billiket experiment. Billiket meaning, okay, I have a couple of objects and one is the indicator. Think that there is one of them creates a sound, and the other one doesn't. And for instance, human beings, we are very good in identifying if I show object A, if it generates a sound, and object B doesn't sound, we understand object A is the one that generates sounds. But it is not always that easy. I can show a picture of both of the objects A and B, and we hear a sound. Then maybe one of the objects hidden behind the other one, and you still hear sound. And in this case, which object? And then you remove one of the objects, like it could be A or B. We can reason about that, but it is indirect, and it's difficult to directly learn such a thing. Humans, we can do very well, but these algorithms, they need to be trained. So this is one of the experiments. Or another experiment question, for instance, which object would the person put next? Which object was thrown by the person? Like we are asking about, okay, what is the object type? Was it like a cup or apple or a ball? So those type of questions we are trying to answer with this model.
Mm-hmm. And so how do these stochastic probes help the model learn about the relationships of these objects and the actions?
So such low-level spatial and temporal details are available in each input frame and in the video. But during the training, if we are not asking these questions, if we are just taking an input frame from a video and encoding it through, let's say, clip or Dino V2 or any kind of these encoders and providing tokenized version to LLM, they do not seem to learn such low-level information, spatial temporal details. So what we do, we actually ask questions during training. Okay, what is the type of the object on this patch, on this image region? This type of questions are asked to algorithm for algorithm to remember, reason, learn, kind of, look, remember, reason is the name of the paper. Exactly. That's what it is trying to learn during the training. So in test time, we do not need to explicitly, have an object recognition or object tracking module, kind of, yeah.
It sounds a little bit like this tweak to the training process is kind of giving the model additional information about what to attend to during the video, what to pay attention to.
Absolutely. It learns what are the important things about what are the objects, what type of objects, what to attend, how they moved, also across the video. It is not just their position and their type, but how they moved in the video. Yeah, exactly. This is what this network learns. Of course, this network also has, kind of mechanism to incorporate such information through its low-level encodings. Yeah.
Mm-hmm. And when you say you're asking questions during training, what does that mean? Meaning you're augmenting your training data set with a specifically formatted question to get at this low-level information?
You are right, because such models, these visual question answering models that uses LLMs and some visual encoders, there are these instructions, question and answer pairs, in addition to given input image or video in our case. Yeah, this is through the training. Keep in mind that algorithm has a temporal attention mechanism across multiple frames, and also, self-attention, special attention for each frame. So it kind of can learn that information. It has capacity, but if you are not asking the right questions, it doesn't focus on those, that information. That's what we are, enabling such models to learn through augmenting the way that we are, in a way, you can think that we already trained the network and then we are fine-tuning the network. Yeah.
It sounds a little bit like a form of curriculum learning in that you're trying to, or maybe multitask also, like you're trying to teach it to pay attention to these low-level features that are important while you're also teaching it this bigger objective. Maybe less so curriculum, but maybe multitask.
No, you have a very interesting point. I'm very happy that you mentioned, Sam. In both curriculum learning and multitask learning, if you want to do supervised version, you need explicitly labeled data, right? And also you like that data to be extracted, available to reason. For instance, I know already where the object is, so there's a detector, and I know how it moved, so there's a tracker, and also I know what kind of object, so there's a classifier. However, we do not want to make it complicated like that. We want this thing to information, the network itself, to naturally ground it with that type of information. So we do not have any explicit detector, tracker, or classifier, unlike multitask learning or curriculum learning. So this is through the capacity of the network, and by asking the right questions in training time, we allow it to pay attention to such details when it is learning its attention mechanism, like the spatial and temporal attention layers that I mentioned.
So the next paper we wanted to cover is called Edge Relight 360, and the focus is text condition 360-degree HDR image generation for real-time on-device video portrait relighting.
That's a long title. This is a generative model which generates high dynamic range image maps, and then we will use those maps in this case, in this paper, as the environment lighting. So since it's 360, we can rotate it around the, let's say, target object, which is a face, let's say, and we know the 3D structure of that object because we can generate the approximate 3D from a single image. So given, let's say, a single image or, continuous video, we know the 3D structure of that object, maybe a talking face, and then the environment this background is automatically generated. It's not like static in my case. So, and also not real, but maybe it's realistic looking, or, you can create an environment which is like space, you are on the moon. And then when we rotate the environment, this 360 image, generated image, lighting is gonna change because maybe there are lights like sun, if it is in the, kind of moon, or kind of in a real indoor environment, maybe windows and, lighting sources. So when you can rotate it. It's a 360 image, and then the lighting is gonna change on the person. This is a very interesting, very natural looking, cool effect, yeah. Of course, the challenge is how we're going to generate these 360 images, because diffusion models, they do not generate 360 images. They only generate like a kind of regular two-dimensional images. Yeah.
The model is generating the entire 360 degree image. Is that from a textual description?
Input is exactly just the text prompt. You actually in this we have a demo about this one also, and any generative AI model we use speech interface. I mean, Qualcomm has wonderful speech encoders and everything, and they are very fast and efficient. It is like GPT-4 So through the speech you describe what you like to have around you, this 360 image, and the challenge is that when we generate this 2D image, the left-hand side and right-hand side is not going to, when we wrap it around, it's not going to, stitch seamlessly, stitch together, because it doesn't know that, kind of these two sides should, when I wrap it around, this is a 360 image, wrap it around, they are representing the same kind of, let's say, part of the scene. So in training, we explicitly impose that. So we can take any baseline diffusion model from, let's say, Stable Diffusion or SDXL, anything you can imagine, and then we change the data set, and we change how we impose like this consistency around on the left and right kind of parts of the generated images, which allows us. Of course, we are using HDRI, High Dynamic Range Image dataset, specific dataset as well. So we can then have a model that can generate 360 images. So that's what we did. And this runs very efficiently on the phone, on mobile devices.
This one sounds like one that you need to see. Is there a video demo available?
There will be a demo actually on device. You can interact with the demo. Yeah, please stop at our booth at CVPR. We have many demos actually. Maybe later we can talk about this.
We'll link to the papers and available demos as well from the show notes page. The next one in this batch of generative AI papers is What to Say and When to Say It, a video language model and benchmark for situated interactions. Another long title as well.
And it's a very interesting title also. And also let me give you an example what it does and what other solutions cannot do, and how this paper contributes. For instance, let's say I have a very respectable LLM, and it is taking also video as an input. And we ask this question, maybe the initial prompt is user should be doing some, let's say, squats. And then also another prompt instruction, provide feedback to the user. We want this model look at myself, and I'm doing some squats, and I ask provide feedback to me, right? The ordinary regular feedback would be, the user, you have successfully completed a squat. This is okay. It is not incorrect. It's correct, but it's not useful. I know I did it. But the version that we are presenting in this paper, what it does, for instance, I'm doing like this squats, and it says, smooth on the way down. It's literally useful information to me because I'm doing something maybe incorrect, and it is trying to correct me. Or when I'm doing something right, it motivates me. It says literally, good job, excellent, awesome. It's like natural, kind of when you go to gym, you have these people helping you. Like it is
Personal
like a
trainer or
human.
coach.
Personal trainers, yeah.
Mhm.
It
So
is not
I'm
like a
guessing
robot.
I'm guessing based on that use case that this grows out of the work of Roland Memisevich and some of the others on his team. They were working on a fitness assistant at Qualcomm and
Absolutely.
prior to their acquisition.
They did excellent job before. They had this amazing data set, and they continue, extending, leveraging that data set for this type of generative AI purposes. By the way, this paper is also talking about introducing a very large-scale data set, benchmark data set, which we call as Fit Coach. There are more than 470 hours of videos, and these videos are organized into 5-second chunks. And we also provide more than 1.7 million question-answer pairs, and also a related model. I mean, we also provide the model, kind of, so people can use it, like Koch Llama model, kind of, and we provide kind of these initial results, numbers, metrics, and everything. So with this paper, I think Qualcomm is contributing significantly to accelerate research in this area, this visual video question answering video models.
Talk about what it is in the approach that is generalizable beyond this specific use case. The idea in the paper, is it about presenting this specific use case, or is it a technique that applies to other use cases as well?
Of course, we had this data set, as you mentioned. That's why we are focusing on this, fitness. This data set is about fitness. However, the model and the lessons learned from this data set is not specific to just fitness. It is any type of activity, action, interaction that a single person or even multiple people would do. The model also we talk about in this paper, it uses 3D CNN. It is a general purpose, encoder to take the video and, generate useful information, which would then go into this language model backbone. And it is also general purpose. So kind of, I do not think it is limited to this application only. You can imagine any other things as well, any other activity.
Is there a distinction worth pointing out here between like fine tuning and instruction tuning? Meaning, when I think about what you're doing with the use case, maybe getting a model to think about the motions and analyze them more critically, I might think of as like a fine tuning kind of task. But being more kind of coachy in the way that it speaks, I might think of it as more of like an instruction tuning kind of. Is that intuition mapped to your experience? And what specifically of those techniques did you apply here?
It is related, very related. Of course, it is not only to improve when we are asking a question to this model, a text question or coming from the speech interface, that it would give a response, but it is also learning to provide feedback by itself. And that feedback comes from the visual data. So I'm doing things in front of this model, and then that model observes me, then provides as a tutor, as a trainer.
There's no specific text prompt that is initiating the model to provide the feedback.
Exactly. Of course, kind of when this model should kick in, provide such encouragement or corrections, kind of is all learned through these high-level questions and, fine-grained questions in the data set that we provide. Yeah.
So the data set might have segments, it will have some coaching instructions, and the model learns to associate that with what's happening in the segment. And then when it's watching a longer video, it might see a pattern that kind of prompts it to coach in a particular way.
Right. And let me give some examples from this data set, what kind of questions they are. For instance, one question could be, is the user going as fast as possible? And the answer is yes, the user is going as fast as possible. Another one, does the user have good form? The answer, no, because not because there's associated video chunk, right? The user doesn't have a good form. And then there are feedbacks also. So these are answers. There's feedback also in this data set. For instance, great job, but watch for your form, or deep squats and 2 punches, get it, and or go deeper in the squat. This type of things, kind of, if you can speed up, that would be great. It is not only question answer, but also feedback.
Is there anything that was required to do to map from question answer oriented data set to, it sounds like the use case scenario does not involve questions at all? Did I hear you correct in that? What I mean is that when this model is in use on a device, it is offering the feedback unprompted by the subject. Exactly. So it's looking at the videos, and when it sees patterns that it remembers from its training data set or similar, that kind of prompts it to initiate this feedback.
Yeah, because it contains these annotations for the feedback in the data set. That is not, for instance, something available outside this data set. This is one of the contributions of this data set. There are feedbacks. In addition to answers, questions, instructions, and answers is the ordinary way of training such models. But now we have also the feedback.
Recently, we heard about this Microsoft recall feature that the idea is to capture your screenshots from your computer and use that so that you can ask questions of what you were doing and do retrieval types of tasks. One can imagine, in conjunction with this type of a model that is, trained on, a video or a set of screenshots, at some point identifying what you're trying to do and then offering you tips for how to do it, more from a productivity perspective than an exercise perspective. There's a bit of an analogy in a productivity oriented model.
Of course, it is monitoring you. I think I didn't use recall feature yet. I need to, test, and it sounds something very interesting. But in general, such models, they observe you through these model tests, let's say screen capture images. And if there is something undesired, maybe there's a problem, or you mistakenly deleted some important information, or you want to just remember what you did, there is some feedback from the user. So that information creates this training data. So here are the, what happened, and whether the person however using the system is happy or not. It is naturally a part of this, training information. It can be constantly learning, or it could be distributedly learning across multiple people. But I think this is a very smart way of getting additional information to further fine-tune, tailor, customize such models, personalize such models.
The next paper is called Math Search, a benchmark for multi-hop step-by-step visual reasoning over plots. What's the challenge there?
Multi-modal models, like the previous one was a video multi-modal model, and this one is, let's say, image multi-modal model. There's an image as an input, and we have this language model, and we are trying to do things around math now. So these models, they take these input images, Sam, and there is something called as image encoder, tokenizer, which could be a clip VIT, or Dino V2, any type of respectable image encoder network, which takes this input image and generates tokens. So it is many of those solutions, they need to scale down the image, and they are looking at patchwise information, texture information in math type of input. For instance, I have a picture of a plot, math plot, literally, maybe it's coming from MATLAB, or some, kind of Excel graph, there isn't much texture, and there are maybe small but important details, like there is a curve, it is crossing some axis, something like that. And the questions that we want to answer, like how many zeros does a function t have? Like where does it crosses the, let's say in this case, vertical axis, or list all the discontinuities of this function. So it has to understand discontinuities and everything. Such information is difficult to learn. So this is a dataset paper. It introduced this benchmark dataset. In the benchmark, we provide more than 200,000 example plots, and we have 2,000 also questions, more than 2,000 questions in the test validation part. So we have single function plots, we have multi-function plots, we have plus within plus, we have multiple plots. So this is a very challenging data set created, put together to allow research, better solutions, better encoders, better fine-grained visual information learning for such multimodal models.
And I got the impression with this one that the sole purpose wasn't necessarily to create models that are better at math or interpreting charts, but also that asking the model to focus on some of the details in these math pictures might help models that aren't specifically purposed to do math better attend to details in other types of images.
Yeah. Because of the current image encoders, visual data encoders, they focus on the global information. And with this, we are motivating, giving momentum to further research that would leverage on the local information.
And was the evaluation and the development, what models did it use?
We have results in the paper on this data set, like how human would perform, how, for instance, there's this LLaVA, which is a model which can take image and text and then do reasoning about that. There is QN, another multimodal model, LMM, large multimodal, some people call it like that. There's also ChartLama, there is GPT-4V, version, visual version. So we provide some baseline results for this, including human performance. We show that there is a gap between human performance reasoning on the mathematical matplots with the gap between human and the existing generative AI models. And the gap is actually quite large, quite big. On average, let's say human does 70% human accuracy, let's say around more than 70%. But these models, even the best one, which is GPT-4V, is around 25-ish, It shows that there is significant progress to be made, promise, we are motivating people to look into this gap and think about better solutions.
The next paper on speculative decoding for multimodal language models. What's this paper trying to do?
There is something called a speculative decoding for language models, LLMs. What it does, there is this, let's say, big model, or, and there is this draft model, tiny model, small model. So big model, we need to load the parameters from memory and do one iteration, then we do another iteration. So it's a big model, takes time. And the token rate, something, how many, outputs, let's say words, you can think that tokens are similar to words, how many words it can generate per second is important metric. We want it to be high, generate many results very quickly, not slowly. So, but there is associated cost of compute with the big model. So what speculative decoding does, it uses a tiny model approximating the performance of the big model. It computes multiple tokens, let's say 3-5 tokens at a time. Then we run the big model just once, as a batch, and we look at their results, and if results are same, then we kind of accept it. We don't need to step by step run the large model. Large model only runs on the batch, which allows us to accelerate significantly. If we look at the results coming from the draft and kind of batch results from the big model, then we can very easily skip, let's say, 2 tokens, 4 tokens if you are using 3, 5, kind of. It is a significant speed up. No one so far tested whether, such speculative decoding idea would extend to multimodal. In this case, we have LLaVA. LLaVA has, we just mentioned, there is like this LLM part, which could be, let's say, Llama 2.7b or Vicuna, any model, any large language model. And there is this image, and both of them goes into the model. The image goes through its own token, so you can ask a question and then it will answer. So the test goal, can we make it faster by adapting speculative decoding like ideas here? And that's what we investigated. We use a tiny model of 150 million parameters, and we observed that we can significantly accelerate up to 2.3 times, using the speculative decoding for a multimodal, not only language model, but multimodal model as well. This draft model could be any model, kind of. It's not this kind of observation. We show that it goes beyond a specific model, big model, draft model. It is kind of a useful information. It shows that SPD, speculative decoding, very easily extends to, multimodal.
And just so I understand, is the draft model, is it part of a larger model for inference? Is it like a subsystem, or is it a replacement model that's been, like it sounds like distillation in a sense?
Draft model is learned to do a good job in approximating, estimating, or predicting, kind of the output of the big model. So we run draft model and we run also the big model. Both of them coexist in the inference time. I mean, it's not like we only run draft model and then, go with its own decision, because draft model sometimes make mistakes. It is, we want it to approximate the big model, but it is not the big model, it's gonna make a mistake. That's why I keep saying on average, sometimes it fails. So if it fails, then you go run the big model, at every, let's say 3, 5 tokens, you don't accept wherever it is not aligned with the big models, batch processing results. We go back to that earlier token and run the big model. So of course, if draft model makes a lot of mistakes, running draft model and then running big model like every token is more computationally intensive. It takes more computation, but on average, if draft model does good job, it can allow skipping 3 token, 5 token, more tokens, So yeah, we have to run both of them. In the inference time, we have both draft model and the big model.
Is the draft model used in inference in training, or just for like plain inference? Meaning, if you're just doing inference, how are you evaluating the output of the draft model to determine whether you need to invoke the real model?
So it generates tokens, draft model. We run it, iteratively, let's say 5 times. We generate 5 tokens autoregressively, not as a batch. So we have this token, another token, and sequentially. Yeah. And then we have the results. One time run of the big model comes as a batch. We generate multiple tokens. We do not do it autoregressively. So there's a danger, of course, kind of. If they are aligned, if they are same, then looks like we are good. But if they are not same, then we need to go to the big model, then autoregressively, sequentially start from that post-generated token update it, and then generate the rest, Because it took for a while for me to understand, appreciate how speculative decoding is working. I was thinking, yeah, you do more computation though, right? Kind of. Then what is important in some cases, we can run this draft model and the large model in parallel on different platforms. And one could be running on MSB or MPU, kind of. The other one is running on CPU or GPU. So we actually do more compute, but then we can very fast generate multiple tokens, Let's say token per second. There's a metric called as TPS. If ordinary big model token TPS could be, let's say, 8, on a mobile device. With speculative decoding, it can go up to 20, 40, kind of. You want to generate results, outputs very fast, But you do some additional computation, or you need to take advantage of parallel processing. That is also a fact. Yeah. By the way, I'm not one of the authors of this paper, but that is how I understand. I would really invite everyone, and a couple of authors will be at the conference, ask questions, if they are interested to our authors,
No, it's a really interesting idea. And in terms of the training of the model, is it analogous to like a distillation type of training, or
yeah, draft model? You mean the draft model
the
training,
draft model?
Right?
Yes.
Yeah, exactly. It is. There's the large model, big model, and we are trying to we are distilling to learn this smaller model that generates similar outputs. Yeah, and distillation is something we do not only for speculative decoding, but also for the large vision models, LVMs or BLMs. We take larger models, bigger models, and we distill them to make them faster. In this case, that is also the reason. Yeah.
It seems like this idea of running a distilled model in parallel with a full resolution model and then checkpointing frequently, that's a broader idea than this particular application of speculative decoding for language models. Is there something that exists like that in vision or in other domains?
Oh, that's a good question. Yes. For instance, kind of this is maybe older, kind of more conventional computer vision networks. There is something called as, for instance, for video activity recognition, slow and fast. Kind of you look at with a bigger model, with using much lower frame rate, the original video, or smaller resolution frames, but more capable model, big model. You run it from time to time, and you run the other one, smaller model, more frequently, and you look at how consistent their results, whether to regularize the, kind of the small model outputs or combine them, fuse them. There is that. There is also hierarchical resolution trees, kind of, and these trees, you have the small version, and you accept small version based on some confidence criteria. If you are not happy, then you will switch to higher resolution. It could be object detector, for instance, in this case, or a segmentation solution. These are more conventional things, but I see the similar analogies, like having a draft model and large model, or having a tiny model but applying many times, or a big model applying from time to time, kind of something like that. And this thing is actually extends to end-to-end training for auto. There are now these models, very interesting areas, Sam. There is these generative AI-based big models that are doing scene interpretation, and there is more conventional, let's say, vehicle detection, segmentation, tracking, like more conventional. And these two, one is kind of high level, providing high level regularization to the conventional pipeline, and like both of them could be estimating the trajectories where the vehicle is going to be in the future. But the big one, of course, bigger, it cannot run real time, kind of at this point. So it is not running all the time. And but they are running together, kind of. So there are similar things all around the research landscape, I guess.
The next paper on our list here is Segmentation-Free Guidance for Text-to-Image Diffusion Models.
Yes.
What's this paper attempting to do?
So this paper applies to text-to-image generation, like Stable Diffusion. You give a text prompt and it's going to generate something. It doesn't require any fine-tuning of the kind of model, but it does. When we run such models, diffusion models, we have the conditioning prompt and also a negative prompt. We do actually initial models. They had 2 runs of the UNet, one with the text conditioning. So it is trying to generate things that you ask it to do, and the other one without any conditioning. It takes the same feature maps and do another run of it, and that is called as kind of like class-free or kind of like a negative prompt. So this information applies to each patch of the image. There's some negative prompting, but let's say we run the network once, a couple of times, UNet, and we now know a spatial region of the image is more representing a given object described thing in the prompt. For instance, the prompt could be a dog sitting on a couch in the kitchen, right? Let's say, I just made it up, and after a couple of first iterations, there are some image regions where you would likely to see a dog, and other parts maybe couch, and maybe the background, the kitchen, kind of. So when we do negative prompting, we are saying the region also penalized for the dog region, penalized for the couch region. So this is kind of like, doesn't sound right? We are trying to generate a dog in an image region, but we are also penalizing for that. So this paper, by just changing the attention map coefficients, these attention spaces are adjusted, kind of solves this problem of, I'm going to generate a dog, but I'm also penalized for the whole thing, kind of. So it doesn't penalizes only for the dog, only for that region. So that's the beauty of it. And when you do that, Sam, when you look at the output results coming from, let's say, Stable Diffusion, and by the way, maybe I mentioned it, this thing doesn't change the, kind of the diffusion model. It applies to anything. It's model agnostic, it's free, it's cheap, it's an amazing idea. So the output images the quality look much better.
What I'm hearing is that it is using this internal ability of the model to do implied segmentation as a way to allow the text guidance to happen in a more fine-grained way, essentially.
So there are different metrics to, measure how good it is. Like some of it we just talked about, FID and clip. There's inception score, IS, and there's also peak score, a network that approximate learns how humans are responding. Kind of someone sit down and, train such a neural network also. That part is automated. So we look at all these kind of metrics, and also we run our own human studies. But we observe that, so here is the base original model, which is a very good model also. It could be, like I said, Stable Diffusion 1.5, 2.1, SDX, or anything. Here is the model. The attentions are changed. Model architecture coefficients are everything the same, like we are doing segmentation-free. So we ask people what would be the better one for you? And 60% of the people with high preference said that I like segmentation-free, and only 19% said that I like the original model. So the gap is 19 to 60, kind of, there's a big indicator that people really like the results coming from segmentation-free. And also in this paper, what we did that, okay, you want to do this kind of evaluations of such networks, and the input is just a prompt, right? And usually there are these prompt data sets like MS COCO 30K, which means that there are 30,000 prompts in a but then, taking all of these prompts results, like for this model A, model B, model C, and showing to people, it is a big feat. It is very expensive. You cannot, ask, a person give me your feedback for 30,000 prompts, Then in this paper, we are also talking about how to make it better to keep the number of human evaluations manageable, not like 30,000, 100,000, but still ensuring that the selected subset of these prompts are representative in terms of the content, and fair, in terms of the model performance. So in this paper, we are also talking about this subset like a benchmark prompt dataset.
So we just made it through the generative papers, and there are even more papers on the traditional side. I don't think we'll be able to get through them at the same degree of depth or coverage. One of the things I noticed is that your team is continuing to investigate the idea of optical flow quite a bit. That's something that we talked about last time. And it looks like several of the papers are kind of continuing to push on ways to do optical flow better.
Absolutely. You are absolutely right. Last time we had another CVPR main conference paper, distract flow was its name. It was optical flow. We put a lot of efforts in optical flow because it's very important, necessary to improve the image quality. For instance, when you take a picture, you actually take multiple snapshots and then you do some kind of alignment to get rid of noise, or improve the high dynamic range, or motion information is essential in compression in anything you do in video, understanding how everything is moving. We are trying to, in this two paper, the first one is the kind of occlusion and consistency aware interpolation. In that paper, we are trying to squeeze all the information we can get from the available limited amount of optical flow data sets. Optical flow is very difficult to annotate. Let's say I have video, I need to go at every pixel, find which pixel it went to, right? It cannot be done manually. That's why there are lots of synthetic data sets, and approximating, computed optical flow manually, this is very, very challenging. So amount of data is limited, Sam, for that reason. So we are trying to do the best. And in this case, that's the difference from what we published before. We are looking at now, we do all type of augmentations. We are trying to, develop the best models in terms of accuracy, and on the leaderboards, Qualcomm is there. But also in this case, we are now looking at, okay, I have 2 frames. What about if I generate intermediate frames? This is video frame interpolation, VFI, and then, generate the corresponding optical flow also, and then let's use it in addition to the original frames, T0 and T1. Now I have T0.68, something like that. And this is now going to give me more information, more frames when I want to go train the optical flow models. 2 things in the paper. How you would get the best these interpolated frames between 2 frames, and then how you will take it and use it to come up with a better optical flow solution, which is model agnostic actually.
And then you've got companion paper in the same, well, not necessarily a companion paper, but it's another optical flow paper called Self-Cleaning Inversion.
The first paper was about how to make it augment data set even with using intermediate frames. And also, we also talk about a better way of self-supervised training. That's separate. Here in this paper, SciFlow, which stands for self-cleaning iterations or inversion. So we are aiming a very efficient optical flow model, which is also accurate. For instance, recent optical flow solutions, most of them are using based on Reft-like idea. It starts with initial optical flow or noise, and then iteratively refines it, using the features coming from different networks. It makes it better and better. But if there's a problem, there's a drift, they cannot correct it. So in this paper, we are introducing 2 concepts. One is self-cleaning iterations. The other one is regression focal loss to look at where during the iterations in inference time, where the model is failing or has potential to fail, because we don't know, because this inference time, but we have indicators, kind of this confidence scores, like this scores, to go change the way that we are weighting the loss in those areas, and also we are handling ambiguities. And also we show that, these methods are, the networks, if you do that, you don't need to iterate many times. It is computationally efficient. It can run real time, kind of. We have a real time running version also on mobile devices. Yeah.
So those couple of papers are, the first one, the optical flow augmentation, is the main conference paper. The SciFlow is a workshop paper. The next paper that I wanted to learn a little bit about is low latency neural stereo streaming, also a main conference paper.
And it's a wonderful idea, kind of. The input is a left-right stereo. It could be multiple also. It doesn't need to be two camera, but stereo or video stream. That's the input usually. But other algorithms do is you can take the left, let's say, and then compress, and then take right, compress separately. So obviously there's redundancy here. Some algorithms, what they do, they take the left frame and compress. Then based on the left frame, they compress right frame. So this is one way. And another way of doing, do left T0, then do T2, then right T1, then T3. This interweaved, fancy things. But this paper talks about parallel hypercodec between this parallel autoencoder architecture, and there's this bidirectional shift module kind of designed to learn the correlation between these left and right branches. So the goal is to do compression together, left and right is compressed together at the same time. That's why it is low latency. And this is important, low latency, Sam, because there are now cameras on the XR devices, headsets, and also autonomous vehicles. You cannot just stream the original video, bandwidth limitation and other things, storage makes it, infeasible. So you like to compress them, but you like to compress them with low latency, very, very quickly. And so how you can do that, how you don't create these dependencies from left to right, right to left, or, interweaved fashion, but do it together and still achieve, for instance, bitrate savings. We show that you can save 50% bitrate if you do it the way that we describe in this paper on cityscapes data sets, or 20 or more than 20%, 15% on Kitty 2012 or 2015 data sets. These are benchmarks, yeah, and it only comes with maybe a little bit more, 35% additional complexity on top of the very simple single stream encoding. Yeah, this is a very interesting paper, useful paper, very practical paper also.
If you've got a left and a right stream and you just use conventional compression, you're kind of leaving the correlation between left and right on the floor. You're not taking advantage of that. And so you could do better from a compression perspective. And so that's why you want to have a stereo aware compression model.
You are right. You actually said it better than me. The thing that I was talking about, this bidirectional shift module, this correlation between left and right, to, compute it mathematically and, then take it out, minimize the redundancies. Exactly. That's what it makes, improves the bit rate, kind of bandwidth bit rate. But also, kind of the fact that we are doing it together. We don't rely on we don't do first left frame compression, then wait for it, then do the right frame. That is more conventional approach. Or do left stream, then right stream is also, kind of like, it is delay, kind of. So this delay is important. We are minimizing this delay by removing redundancy.
we are going to leave the remainder of the papers as an exercise to the listener. We're going to have them all listed on the show notes page. There are, as I mentioned, a bunch more. In addition to a number of demos, you mentioned in passing the demos that you're doing. Are there any particular demos that you would want to call out?
Yeah, absolutely. Please stop by. Many of those demos are running on device, on phone, kind of mobile devices. And one of them is something we did, LoRA, with stable diffusion. LoRA is low rank adaptation. For instance, I can take original model and make it to generate better faces. It is fine-tuned on faces, or it can generate, any kind of, let's say, cartoon characters, better. It stylizes with some kind of intended style. But the challenge is that this additional LoRA coefficients, I have a big model and a small model, LoRA coefficients, adaptations. If I fuse them, if I add them, and then run them, if I change, then I change my mind. I decided to impose more of the style, less of the style. I cannot do it. I have to go back and refuse it again. And these are big models, kind of several billion of parameters. Doing that fusion and then loading it again to, memory, it's going to cost me in terms of time. I cannot do it very fast. It's going to take a couple of seconds on device. So this first demo shows that you don't need to wait. You can really easily switch, to change the degree of this, how much you're going to impose. And also you can very easily switch from one LoRA to another LoRA and another LoRA on the fly, kind of. This is a very cool idea. The second one is mobile LLaVA. For instance, you can take a picture of yourself, anything, the scene, and then any object, you can ask a question, and then it will answer. For instance, you are taking a picture of, okay, what can I cook with these ingredients in this picture? And it will tell you what you can cook. And then you can ask, this is the dialogue model, how many calories will it be? Kind of something like that. And you can imagine, kind of like, you can literally have a conversation with it. And it's running on the mobile. It's available as of now. This is something we recently developed. And there are other demos. For instance, like the demos that goes to our autonomous driving stack. Very interesting. We generate new samples, augment the data with, for instance, there's a scene and we put animals in the scene, virtual. They are not real, but when we put them, then we use that data to train our stack detectors, then we show, oh, they are improved. And in some cases, it's very difficult to collect such data. But also things around, let's say, more core computer vision, segmentation on device, segmenting anything and tracking anything on device, or like I said, portrait relighting of the faces, or generating avatars, talking avatars on the phone, or kind of AI assistant with a avatar face. Kind of, there are cool demos. Yeah, stop by.
All right. And before we wrap, you also, you meaning Qualcomm, also coordinated a couple of workshops at the conference. Tell us a little bit about those.
Yeah, absolutely. The first one is the first conference, first workshop in this area. It is efficient large vision models, CVPR. They are becoming very, very popular. But also, kind of we more and more need them to run on edge devices. So we co-organize this workshop with many other, companies and institution, academia. And please stop by. You will see, how these efficient transformer architectures for large vision models or foundation models, generative models, multi-modal models are kind of making their ways into such devices. And the second one is called omnidirectional computer vision, and this is a very important area because it applies to many use cases, from augmented reality to any camera system for automotive surveillance, photography, and now these solutions that we look into in this workshop is focusing on such input coming from these omnidirectional cameras. And this is maybe the maybe third or fourth issue of this workshop. Yeah.
Well, Fatih, thanks so much for taking the time to share with us all that you've been up to and what we can look out for at CVPR.
Absolutely, I'm very excited about it. Thank you so much for having me, Sam. And this is a great podcast. Thanks for inviting me.
Thanks so much.